Login accepted.
Hello everyone, my name is Tomasz Jędrzejewski. I'm a principal software engineer working for Allegro. Allegro is the biggest online marketplace in Central Europe. It originated in Poland, in Poznań. Now it is an international company, and it also has an office in Krakow where I work and live. So today we are going to talk about measuring data, metrics and alerts. What do you know about your metrics? This is the title of my today's presentation. So regarding the agenda, we will start with talking a bit about statistics and metrics. Then we will go through limitations of monitoring systems. And then we will try to deal with complexity of applying this knowledge in our everyday work. I will show you some useful heuristics that I introduced in my team based on my personal experience. And then at the end, we will talk a bit about alerting thresholds. I will also share some hints that I collected during my work. So probably some of this knowledge may be obvious for some of you. Well, you are very lucky. Because my observation shows that on the one hand, this is a very important aspect, especially when it comes to developing distributed systems. And there are many developers, many engineers who don't have the necessary experience, didn't have actually a chance to get it. So I will begin this presentation with some personal story. You see, we are all engineers. In fact, some of us, including myself, may even have a formal university degree in engineering. And this is the definition of the engineering I found on the internet. So the practice of using natural science, mathematics, and the engineering design process to solve technical problems, increase efficiency and productivity, and improve systems. One of the important fields of engineering is applied metrology, the study of measuring. And I looked at the programs of various engineering faculties at Polish universities. And yeah, I noticed that many of them actually have the classes of applied metrology, but computer science does not. In fact, I was actually very lucky that I had statistics, but it was only a pure theory with no connection to how to apply this knowledge to distributed systems. So I started my first full-time job. I graduated from university, and one day I attended the conference and decided to ask some questions to the keynote speaker. Those couple of questions turned into a longer conversation. We were chatting. Hello? Oh, yeah. We were chatting, and suddenly the speaker asked me a question, what company I was working for. I told him the name, and he told me one thing. You see, I was once consulting and working for your company in the US, and I didn't actually like the technical culture over there. Why? Because your engineers didn't measure things. Actually, this conference happened in this particular venue. In fact, it was on this corridor right there, so this is actually a bit special place for me to be able to speak about it right now, because that conversation was a game changer for me. Basically, he gave me a lot of examples of how other companies backed their decisions by data and experiments. So I decided to, okay, I want to be that guy too. I don't want to be the engineer who doesn't know how to measure things. But here I found the first obstacle. I looked at my then project, and I realized that there was actually nothing interesting to monitor, measure. We had no data. We were far away from the actual customers. And it took me a while by trial and error until I found the right project when I could actually start developing my skills. So no doubt that so many engineers don't know how to do it if things look like this. Even now, such situations happen in Allegro that, for example, recently, a team leader of a newly formed team came to me and asked me a question. Tomek, we are going to production soon with our first service, but we don't have experience with alerting, with monitoring. Can you give us some advice how to do it? Yeah, so like I said, if you already know those things, you are very lucky and I'm very happy for you. And my observations shows that there are plenty of people who didn't have a chance to get it. So hopefully this presentation is especially for you. I will show you how to start, what to look at in order not to get lost with this. So let's do a small experiment. I will show you 4 charts of response times from some endpoint in some service. And your goal will be to tell which one is the most accurate, which is the most correct. So this is the first chart. We can see that the response times are around 55, 40, 45 milliseconds. Sometimes it goes to 60 or so. So probably we could say that these are pretty good response times. Now let's go to the second chart. Well, over here the situation is a bit more dramatic. So at the bottom, we start at 100 milliseconds, and sometimes we get as high as 800 milliseconds. The interesting thing, maybe some of you have already realized it, that those 2 charts have been generated from exactly the same endpoint, exactly the same service, exactly the same data points collected at the same time. But we see 2 completely different response time charts. Now, the third one, we again dropped below 100 milliseconds, but this chart is different than the first one. And the fourth one, this one is pretty similar to the second, but the peaks are not so sharp. So what's going on there? It's obvious that depending on which chart we are looking at, we can get into completely different conclusions about the health, about the state, about the performance of our service. So probably some of you think, oh, maybe he manipulated with percentiles. Here's 1 percentile over there, the second. Well, yes, there are differences in the percentiles I used, but they actually are not attributed to the biggest differences here. So let's reveal the actual Prometheus PromQL queries. So they look like this. We see that, yeah, we have the quantile 99.9% in the top. At the bottom, we took the maximum times. But the biggest difference was because on this right side, I used maximum function, and over here I use the average. In fact, there is little difference between maximum and P99.9 response times. So the same data, completely different results. And which one is the most useful? Well, in fact, none of them is fully accurate, and let's stop over here and see why. So let's talk about averages and arithmetic means, because we see that this made the biggest difference here. Well, many blog posts on the internet, there are many of them that tell us why we shouldn't average percentiles, why it doesn't make sense. I also found one article of why it makes sense, but only under certain conditions. And in my personal opinion, yeah, the average is only one side of the problem, and probably not the most important one, because in statistics, the average is an estimate of a central tendency, and arithmetic mean is only one of the types of the average. We also have geometric means, weighted means, and so on and so on. The real problem is that for the majority of the population, arithmetic mean is the only statistics term they know. So they try to apply it everywhere without looking at whether it actually matches the conditions where it is the most useful one. And that's the real problem here. Basically, you can hit a nail with a hammer, but you certainly don't use it to cut a loaf of bread or solve personal relationships. Well, I don't recommend that one especially. And let's take a look at those three data sets on two charts. I picked up the data points in such a way that in all three cases, if we try to compute the arithmetic mean, we will get exactly the same result, 8. But we see that we have completely different data here. When it comes to this one, this chart on the left, well, probably we could say that 8 is a pretty good estimator. If we look at this chart, we intuitively feel that, well, 8 tells us something about this. But when it comes to those two charts, we see that there are completely two different situations. And suppose that one of them is critical for us, the other is not critical. And if we, for example, try to create an alert threshold based on this average, we wouldn't be able to distinguish those two situations based only on the arithmetic mean, because either we would capture both situations, or we wouldn't capture any of them. For example, if we set the threshold to 11. Okay, so we see that arithmetic mean is useful only if our data have certain distribution, have certain characteristics. So how it applies to our percentiles? I prepared an example, an exercise for us. Basically, let's imagine a situation that we have a service with 4 instances somewhere in our infrastructure. And in a certain observation window, we counted 600 requests. We measured response times for them. So basically, I generated some response times to match those characteristics. This is basically a histogram, so that I have, for example, 126 response times in this range for this instance, and so on and so on. And let's say that our SLA is that 99% of our requests should be below 500 milliseconds. If we compute the actual P99, we will see that, yeah, we meet our agreement. Because we would get the result like this for this particular data. Actually, this experiment is pretty easy to do by yourselves. If you know Google Sheets or Excel, you should be able to do it by yourself within 10 minutes. So I encourage you to do this exercise for you. But the problem with this value is that to compute it, we need the actual response times of those 600 measurements. But this is what is actually exported to your monitoring system. Instead of exporting all data points, that could be quite expensive, we compute local P99s for every instance, and we only get those 4 numbers. And we see that over here, for example, for instance D, we exceed this SLA, but does it mean that the general P9 SLA is not met? Okay, so here is the real problem with this. Percentiles are the terminal values, so basically this means that we cannot take those values. There is no aggregation that would give us this value. Every aggregation that we'll try to use on this data would poison it. So it will introduce some poison, some deviation from this value. And let's see which one. So let's try to compute the average. We would get this number. Well, it's close, but it's not the same. Maximum, well, we will get this value. If we try to use maximum, we would think that we exceed our, we don't meet our SLA agreement. Maybe median. Well, another value. Actually, average could be a pretty good estimator of what's going on here. It wouldn't give us this value. It could be useful, but only if the distribution of requests among those 4 instances would be uniform. But we see that it is not. So instance D gets the most traffic. Instance D, there are only slightly more than 100 requests. And yeah, in real systems, we usually don't have uniform distribution of requests among our instances. Depending on how our load balancers are configured, they can, for example, try to offload instances that cannot catch up with processing the incoming requests. So it may happen that, so this is a real situation. And we see that this actually can affect our P99. So I made this change that I decided to move some of those response times to instance D, just to show you the difference. For actual P99, it shouldn't matter what the distribution of our requests is. Actually, it doesn't matter how many instances we have. We should always get exactly the same value. But if we do our local P99 computations, we would get completely different results. And in fact, if we try to aggregate them again, we see that again we get different values. So what's the conclusion over here? Does it mean that those 4 charts that I showed at the beginning have no value for us? Well, they have some value. If we understand how our data is poisoned, they can give us some general overview, look and feel how it looks like, but definitely we cannot use them to implement our SLA. How we can deal with it? The first thing that we can do is rewarding our SLA. So this was the original definition. P99 response times below 500 milliseconds. Let's reward it to the percent of responses with response time below 500 milliseconds. It should be 99%. What does it give us? Let's notice that we don't change our SLA, it's just rewarding. The values are the same, but now we can implement it differently. What we can do is basically creating a simple histogram with 2 buckets. The first bucket would be the counter of all requests that below 500 milliseconds. The other bucket are all response requests above this value. And this is enough to compute whether we are in those 99% or not. And the counters have a couple of useful attributes over here because they are very easy to aggregate. So it's very easy to take the counters, local counters from all the instances and simply compute the sum of them. And it's enough to compute our SLA. They are also much more reliable in the monitoring systems. They are not perfect because of the limitations of monitoring systems themselves I will shortly tell you about, but definitely much more reliable than attempts to aggregate the percentiles that we did earlier. The tip over here, if you try to create a histogram, do not create actually more buckets than you need. It might be, for example, interesting for us to why only 2 buckets if we can have more and we could have a better overview of what's going on. But remember that these extra buckets are the extra data that needs to be exported to our monitoring system. If you are on public cloud, you will pay for it. If you are on on-prem infrastructure, well, you will also pay for it, but in a different way. For example, you don't want to see how your monitoring repository dies because of too much data exported by services. So this is why you should only create buckets that you are actually going to use. So I mentioned the limitations of the monitoring system themselves. Let's remember that these are just tools. They are also subjects to various technical limitations of the storage, of latency, and so on and so on. And in Allegro, we are using Prometheus and the Victoria metrics to store and process our monitoring data. And Prometheus works like this, that it works in a pool model. So the instances expose the current state of all counters, timers, and so on a special endpoint. And there is a scrapper which periodically gathers this data and puts it into the central repository. So Prometheus tries to do it in regular intervals, for example, 1 minute, but the instances have no guarantee that the next scrapping will take part exactly after 1 minute. So the actual observation window might slightly vary between instances, and moreover, there might be some shifting between instances. So we don't have a guarantee that all 4 instances will be scrapped at exactly the same moment. For example, instance B can be scrapped 10 seconds later than the instance A. So our observations windows don't overlap. And these are the technical trade-offs, technical limitations that we should be aware of. This is why I said that the counters are more reliable, but not perfectly reliable. One extra thing about counters is that we are usually not interested in counters themselves. We are usually interested in how those counters change over time. So effectively, what we want is the derivative of the counter. But to compute the derivative, we need at least 2 data points. And this is a common problem. That, for example, engineer observes that the instance dies immediately, and sees that the counter had the value of 3, but there is no data in Grafana. Why? Well, for example, because this instance didn't manage to export the second data point, and we have not enough data to compute the derivative. So this is also what we need to be aware of. And here we touch another issue. Basically, we often create our metrics, we configure our dashboards, alerts, and so on, when everything works fine. And we forget that we are not making our metrics to make us feel good. Yeah, it's nice to look at those dashboards and see how data is flowing and so on, how many requests we are processing. But the real test happens when something goes wrong. The metrics are here to assist us to when things don't work as expected, where something fails, we don't know why, and we may expect absolutely everything. And let's remember that when an actual emergency happens, we may be tired, we may be woken up in the middle of the night, we may have angry stakeholders behind our backs, and in this condition, it's very easy to miss out very silly things, make silly mistakes, make silly judgments about the situation. So this is why it is important to be very explicit, to make our charts really good, really useful in this particular situation. So we should be very explicit about, for example, chart names. System performance or memory usage are not good names for our dashboards, for our charts. Let's note down the aggregations that we use, because we see that they matter here in order to understand how to interpret the data. Let's not remember about proper units of measurements. This is something that I see that many engineers often forgot. I had a personal story that once I configured a 3-week timeout because all the configuration options in the systems accepted integer timeout value, which was milliseconds, but one single option accepted seconds. So yeah, it happens. Try to avoid cryptic abbreviations that only you understand. Use full words. And finally, note down the place of the observation, whether this is an insider or outside the observation. What does it mean? Let's take a look at a simple diagram. So if we have a distributed system, we probably use a service mesh. We have some sidecar, and the traffic comes to our service, to our instance, through this sidecar. And This instance reports the incoming traffic, so how many requests come, how many errors there are, how many successful requests. It reports on CPU and memory usage. But let's remember that this sidecar can block some requests if the configuration tells it to do so. And if it happens, let's remember that this instance won't see that there is a request which didn't reach it. If we base our metrics only on this data, we won't see that there are requests that are blocked. In fact, we once had the situation that there was a typo in the configuration of the sidecar. It blocked a tiny amount of requests with 403 forbidden error, and we noticed it after 1 year by accident. It turned out that nobody actually looked at how it looks at sidecar perspective. There was no monitoring here, no metrics. In fact, the metrics were not accurate enough to distinguish 403 from other errors. So basically, we forgot that, yeah, we should also look at external observation of what's going on. The same is with CPU. The instance can report the CPU usage, memory usage, but if it dies, it may not have enough time to report that, for example, there was a sudden peak. This is also what happened to me. I deployed a new change to a testing environment and started generating some traffic, and the instance instantly died. I looked at the memory usage chart, so nothing suspicious, and it took me literally an hour to realize that I'm looking at the chart of the JVM heap usage. Then I connected the dots that if this is generated by JVM itself, which dies, and there is a Prometheus which scraps every minute, I won't see this peak because the instance dies before the scrapper gets it. I had to look at Kubernetes metrics, and I saw the peak, and I also saw my termination reason. It was just in front of my eyes. I was simply not looking at the right place. So we see that there is a lot of complexity going on under those simple metrics. And it makes a problem for us where we try to create an error reporting. Well, it's very easy to imagine that the developers will forget about it if they had to think about all those details every time they want to create a handling of a new error. So how can we deal with it? One thing that I did with my team was trying to educate ourselves. So we started making weekly meetings for 1 hour where on-duty engineers discussed the recent emergencies, recent alerts. They told how they diagnosed the problem, shared their experience. Based on this, we looked whether our metrics, our dashboards are good enough to deal with the situation. We fine-tuned them, we fine-tuned our error handling. What was also useful, we started writing incident playbooks. So if there was a problem that happened more frequently, we note down the procedure, how to solve it. We also practiced chaos testing. So if you have chaos tests, use them to verify if your dashboards can capture this, if your alerts can capture this. If you cannot simulate certain failures, what is useful is role-playing. One time we had to onboard a new engineer, and what I did was I simply took the scenario of one failure and we played a role-playing game where I was a game master. I described the situation. For example, you have been woken in the middle of the night by the alert. What are you doing? He told me what diagrams he would look at, showed me them actually, and so on and so on. And this was a great tool to get him familiar with all the tooling, with all the steps, with whom to contact with, and it helped us dealing with the alerts that we couldn't produce ourselves quickly. And the last point, if you find a general solution to some monitoring problem, some error handling problem, try to build a convention around this to help your engineers applying this in real life, so they don't have to reinvent the wheel each time they, for example, introduce a new error. So now I'm going to show you a simple heuristics and an example of such conventions that we introduced in our team based around the HTTP status codes. This is a convention. It worked for us. It was tailored to our needs. Maybe it will work for you as well, but it doesn't have to. You may find it inspiring, but you may need to adapt it to your situation. Maybe you will just take the general idea of how we got to this. It's just an example. So let's remember about this and what was the starting point for us. So the initial question was what to monitor. 500 responses, 400 responses, and can we use any 400 response for our purpose? It turns out that not. Most of HTTP status codes have very precise semantics described by the specification, and this meaning is tightly related to the HTTP protocol itself. So we shouldn't use it for representing the errors in our logic. In fact, for me personally, even the popular error 404 not found is quite problematic, because let's notice that we actually have two situations here. One, for example, an entity doesn't exist. The user doesn't exist, the product doesn't exist, and so on and so on. But there is also a second kind of problem. We may have made a typo in the path. And this is a completely different situation with completely different mitigation strategy that may require change in our code, in the change of the code of our client. But we use exactly the same status code to represent those two situations. So we effectively cannot distinguish them. So now we defined 4 classes of errors that we could have. So first class are crashes, null pointer exceptions, basically everything that we introduce into our code, we need to fix it ideally as soon as possible. Then our service usually communicates with other services, with databases, and so on and so on. And those services may experience an outage. There might be some transient network errors. So this is the second class of errors, outages. The third class are the client errors related to HTTP protocols. So our client might not send proper headers, might forget about something. And there might be some misconfiguration. And the final class of problems are client errors related to the logic, so validation errors, entity not found, trying to do some action when the system is in the wrong or not valid state. And all those classes have different mitigation strategies. How we can translate it into the code of our service. In Allegro, we use hexagonal architecture for the majority of our services. So basically, we decided to map those observations into hexagonal architecture. In hexagonal architecture, basically, the domain logic is separated from the outside world by ports and adapters. On one side, we have downstream services that call our service, and those calls come into controllers. On the other side, the domain logic may trigger some actions which require contacting upstream services through, for example, HTTP clients. This also can be communication with database and so on. So we can see that those 4 classes of problems originate in different places of our application. In controllers, in basically those adapters, here we get HTTP errors, validation, authentication errors. Domain logic also produces 400 errors, but they should be related to our domain logic. When it comes to communication with upstream services, well, we decided to distinguish between outages and everything else. We spent some time looking for the best status code for outages. Eventually, we stick with 502 bad gateway. I'm not sure if this is the best choice that we could do, but yeah, basically we chose it. And 500 is everything else. So all crashes and everything that we forgot to or missed when it comes to handling. So now what we can do is simply creating an exception hierarchy in our application and teach our developers how to use it. So here we have API exception, and we map it to those errors. HTTP errors are usually handled by default by the framework itself. For this side, we have external service exception, and here domain exception with some specializations. This looks like a very simple and very obvious things, but I see that many developers have all those tools in front of them and simply don't combine them together into a single working mechanism, effectively getting a pretty random experience when working with errors. And it's all about conventions. So if developers see that the final behavior is predictable, then they start to trust it. And if they start trusting it, they intuitively start using it. If they need some specializations, they easily can create a dedicated custom exception, create an exception handler for it, exception mapper for it, and spend some time defining the proper behavior. If not, they have a default behavior which is maybe not perfect in all situations, but it's good enough for the majority of cases. And it helps them reasoning and focus on solving the actual problem, implementing the actual feature without too much overhead. So this was our strategy to deal with complexity. What is also interesting about this approach is that we can easily validate the proper usage of those exceptions with, for example, arc unit tests. We can easily check whether they are thrown in the proper part and block attempts to use them in wrong places. So the tooling, the arc unit, also helps us enforcing this policy, even if someone forgets how it works. Once we have exceptions, once we have proper status codes reporting to our monitoring, we can get into defining the alerting strategy for them. So we see that those 4 classes of problems turned into 4 classes of HTTP status codes. So first we have 500 internal server error. These are our crashes, these are our unknown things that we forgot to handle. And here I recommend to setting the alerting threshold to 0. It may sound scary and aggressive, but let's remember that we want to get rid of them as soon as possible. We don't want them to accumulate in our service, especially in rare corner cases. And let's not be afraid of it, because if these are changes, failures introduced by recent changes, we don't have to make complex reverts. We can usually very simply revert to the previous version of the service if something goes wrong. So even if the engineer is woken up in the middle of the night, what they can do is simply deploy the previous version and get rid of the problem. The deployment culture also helps here. So, for example, we decided not to deploy on Fridays, or if deploy on Fridays, only on the responsibility of the on-duty engineer. So if I were an on-duty engineer on Friday, I could take the deploy that my own change and take the responsibility if something goes wrong. If we had more risky change, we try to deploy it in the morning so that we could have the all-day observation window to see if something goes wrong. We use canary releases to check if everything works fine. So it really helps, and it really helps keeping our service in a good condition. When it comes to bad gateway, here we wanted to tolerate some amount of those errors in some reasonable time. Why? Because those errors can be usually mitigated by some automatic strategies, such as retries, circuit breakers, and so on. So the engineer should be involved only if those strategies don't help. So this is why we should be tolerant. Many of them disappear very quickly because there may be some transient network errors. When it comes to HTTP protocol errors, well, here I would say that it depends on who our client is. If this is a public API and a third-party company, well, we may want to tolerate a certain amount of these errors because we don't control these guys. We don't know what they are doing with our API, and we don't want them to wake us up in the middle of the night because of some silly mistake. Of course, if the traffic goes too high, we should get involved because this may be something suspicious, but generally we want to be tolerant about this. When it comes to internal clients, we may consider setting also the threshold to 0. Why? Because this may indicate that the second service, for example, made a typo in their HTTP client code. It means that something doesn't work in our system. So even if this is not our fault, we may want to solve it as quickly as possible to make everything work properly. But yeah, it all depends on the context. It all depends on our situation, what we should do. And finally, application logic. Here I recommend the high tolerance because, yeah, this is something normal. This is normal that people make mistakes in the online forms. They make validation errors. We don't want every single validation error to alert us. However, I still recommend to set the alert, but on very high threshold, because, yeah, it's normal. Like I said, it's normal that, for example, 5% of those requests are wrongly filled forms and so on and so on. But if it suddenly goes up to 80%, 100% of the traffic, it may mean that we introduce a bug and our validation doesn't work. And suddenly everyone have problem. So yeah, be tolerant, but still monitor. And you may have noticed that sometimes I use absolute threshold, sometimes percent-based. Which one to choose? Well, the answer is it depends. And it's not just a consultant way of telling get off. It really depends here, because take a look. If you have a big distributed system that is exposed to the public, even if you have the high traffic rate, it's not uniform through all day. At least not if you operate in a single time zone, in a single country, or a group of closely collocated countries. Usually you have high traffic in the day and very low traffic in the middle of the night. And let's see what happens here. Even if our errors are proportional to the total traffic rate, this indicates that we should use percent-based thresholds. This strategy would fail in the middle of the night because we may not have enough requests to compute those percents accurately. So a single request may comprise 100% of all traffic in the given observation window, and we get an alert because of a single wrongly filled form in the middle of the night. So basically we see that those strategies vary depending on whether we have low or high traffic. One thing that I do not recommend if you want to introduce such a switching this strategy is not configuring it against the hours of the day, because this is how I once generated an alert for myself at 10 p.m. I simply didn't realize that the traffic at 10 p.m. is still quite high and my absolute threshold is not sufficient for this. And here's some simple decision tree that you can use to determine which threshold is better for you. Basically, if your traffic rate is low, you can check whether these errors are proportional or not to the total traffic. But in case of low traffic, it's better to stick to absolute thresholds in order to eliminate false positives. When it comes to large traffic, again, we ask the same question, but here we can make two different decisions. And finally, we have critical errors here. Like I said, we want still to have a threshold, absolute threshold of 0. Of course, this is still a heuristics. It may not exactly work for you. You may find something different or slightly different, more useful in your case. It's just an example how you can manage the complexity of all this error handling in your systems. the most important thing is to start, is to finding the similarities, finding general solutions, and finding general observations about how your system behaves. It doesn't have to be perfect. It has to be, because false positives are basically unavoidable, but you can easily get them into the manageable level. Yeah, so to wrap up, there are basically 4 things to remember from this speech. First of all, if you only heard about arithmetic means, try to extend your knowledge about statistics, because this is important. Without it, you won't understand what's going on here. Remember that metrics monitoring systems are not perfect. They are still tools. They are made by humans. So not only there are technical trade-offs, there may be bugs, there may be errors in the documentation. These tools are still made by people who make mistakes, and don't take everything as blessed. Even if you have a team in your company that provides the predefined monitoring, predefined metrics, predefined alerts, they are also humans who can make mistakes. If you find something, just ask them and discuss, report the issue to them so that they can improve the system. But don't treat those predefined configuration as 100% ideal, because ideal is not possible. Remember that we don't make metrics to make us feel good. Let's validate our dashboards, our metrics against actual failures, against actual problems. And finally, let's try to find general solutions, general approaches to certain classes of problems, and build conventions around them to help your engineers focusing on the right thing, writing working software that solves the actual problem. Yeah, so that would be all from my presentation. I hope that you found a couple of interesting things or thought or ideas here. Don't forget to visit our Allegro Tech blog under this address, where Allegro engineers share their experiences. And if you want to stay in touch with me, I will be hanging around over here, sometimes in the on other speeches, sometimes on the Allegro stands on the first floor. You can also reach me out on LinkedIn. Yeah, and basically, thank you very much for attending, and I'm very happy that I could give this speech to you.